Okay, so maybe I will start and introduce our speaker of the day. So hi everyone. So today we have the pleasure of having Dr. Manuela Temmer, or I should say professor, I don't know.
All fine, all fine.
So she obtained her PhD in astrophysics from the University of Graz in 2004. Actually, I'm not sure. Was it also on CMEs or?
It was on sunspots, actually.
Oh, on sunspots, okay. And then she completed her postdoctoral research at the VAR Observatory of the University of Zagreb in Croatia and the Space Research Institute of the Austrian Academy of Science. So she was a senior research fellow at the Lockheed Martin Solar and Astrophysics Laboratory in Palo Alto in the USA. And it's since 2010 that she was appointed as an assistant professor and successfully defended her habilitation thesis in 2015. And then was promoted to the rank of associate professor at the University of Graz in October 2016. And now she's leading research on heliospheric physics, the research team of the heliospheric physics in Graz. And so today she will give some interesting talk on CMEs and space weather. So I think you can start sharing your screen.
For introducing. So let's see. We managed before. So should we do it now? Okay, I guess you can all see my screen. So first of all, thanks for the invitation. Also, thanks to Paul for suggesting me to giving the seminar talk. Very exciting to give this talk to a community which is not fully familiar with solar-terrestrial relations, I assume, or with solar physics. I mean, the sun is a star as well. But as I learned also from colleagues like Paul, we are talking about the same things, but having sometimes also a bit of different language. So maybe we can make the barriers a bit lower for today. So I would like to talk to you about solar-terrestrial relations, especially coronal mass ejections, flare emissions, and how they actually influence the Earth atmosphere, and how we tackle the issue of forecasting those events and phenomena to be prepared for really geo-effective space weather events by combining remote sensing image data and in-situ measurements. So the sun is an active star. We see here in the image, this is an EUV image. It's a composite image of two different wavelengths, meaning two different temperature ranges, but it basically shows temperature range of about 1 to 2 million Kelvin. So typical for the solar corona. We can see here bright regions and loops, magnetic loops, that are in principle so-called active regions on the sun, and they have underlying a very strong magnetic field. And in this magnetic field, there is a lot of energy stored, and this energy can then be released within minutes. We're talking about total energy release of 10 to the 32 erg, and it can be released within a few minutes, so very violently. This emission is ongoing. You see then an increase in the flux, in the intensity over all wavelength ranges. So we're talking here about even white light emission is possible depending on how strongly particles get accelerated. But we also see it here, as you can see in EUV, but also in radio wavelengths. So it also can produce gamma rays. So it depends how strongly these reconnection processes are ongoing or how fastly. Coming to coronal mass ejections. So mass ejections are related to flares, to these emissions as we just saw them. They come from basically closed magnetic field structures, as you have seen them in the previous image, these closed magnetic loops. And there is some instability or reconnection process that causes then the eruption of density, of mass, and magnetic field. So a coronal mass ejection is basically a magnetic flux rope that has plasma closed within this flux rope, and this whole structure is then erupting. It is usually CMEs and flares. They are very closely related, so they belong to the same phenomenon of magnetic reconnection, or as a consequence of magnetic reconnection. There are typically, we observe for CMEs, I guess you can see my mouse. We typically observe CMEs with a few structures. Those are the so-called shock sheath structure. It depends on how fastly the CME erupts. If it overcomes the ambient speed, it produces a shock. So this is seen here by this very by this sharp front, followed by a sheath structure. That means in the sheath there is plasma. Density is piled up, so compressed plasma, which is then seen in this white light coronagraph image as a high intensity structure. Then it is followed by a so-called void. In this void, there is the magnetic flux rope embedded, because the magnetic flux rope has a magnetic pressure inside. So that means lower density, and that's why it appears darker in this white light image. And sometimes you also see the core of a CME that is usually related to filament eruptions. So all in all, it's in principle a huge structure that is then able to propagate in interplanetary space. And here you see coronagraph images in animation. So we see here, as we have seen before, the EUV image from the surface, where we see these brightenings, the flares. And as a consequence, then the coronal mass ejections that are coming out here. Here you see it very, very strongly propagating also into the direction of Earth. So this satellite is sitting in between Sun and Earth, so 1.5 million kilometers ahead of Earth. And so this is Venus, I presume. These snow snowflakes that you see in the CCD camera are already particles that get accelerated to almost speed of light. Some of them get accelerated to 70–80% speed of light. So those are the first, so when we have eruptions, those are the first particles that actually hit the camera and also then can penetrate into the Earth's atmosphere, where they can have geoeffective, where they are geoeffective. We also have dependence on the solar activity cycle. So the sun has an activity phase of about 11 years. During the maximum, we have a few CMEs per day. During minimum, it's only a few CMEs per week. And so we expect, especially during the high activity phase, very strong space weather effects. So that's why it's very interesting heading into towards solar maximum, but that also makes the whole interplanetary space more structured and more complicated. And with that, understanding the physics is more complex, and also the forecasting is more complex. So when we talk about observations in CMEs, we have quite some complicated situations, because the CMEs are optically thin. So what we actually observe are line of sight integrated density structures. Here you can nicely see in a 3D reconstruction of, so we're talking basically about a 3-dimensional body that is projected onto a 2-dimensional plane. And here we see this 3-dimensional reconstruction of this geometry of this CME structure. And in the observation, you nicely see this projected observation. So that's the observation that we have. And in reality, or at least in theory, if it's an ideal geometry that we assume, it actually looks like that. But what we observe is only the projected part. So this makes measurements extremely uncertain. So we have high error bars that we have to put on on all the parameters that we derive. Is it the width, the size of the CME, a propagation direction of the CME, the speed of the CME? All this is affected by projection effects and has large uncertainties. And which it makes forecasting very complicated. Also, we have a shock sheath structure that we observe and a flux rope, and we know that the flux rope, so the magnetic field that is embedded, is the part that makes the most intense geomagnetic storms. So this is the part that the structure that we would like to understand better, because with the magnetic field interacts with the Earth magnetic field and again produces here reconnection and particle acceleration that then leads to ground-induced currents, power outages, and things like that. But this is since it is embedded in a structure, in a dense compressed plasma structure, it's quite hard to track the magnetic flux rope. Complementary to remote image data, remote sensing image data, we also have in situ measurements. So that means we have at specific points in interplanetary space, we have satellites with instruments that are able to measure the plasma and the magnetic field of the solar wind. So that also means when there is a CME hitting this instrument or sweeping over this instrument, we're able to get signatures of the coronal mass ejection. That means, in principle, we have here localized measurements. You can imagine this like the needle in the haystack. You have a needle that, or one of the haystacks that has a specific orientation. The needle measures this orientation, and from this specific localized measurement, we would like to reconstruct the entire structure of the haystack. So that's a bit complicated, but with new complementary, so combining remote sensing and in situ data, in the past years we were able to get a pretty good idea how these localized structures can be related to the larger structures. You also can see here instruments in the meantime cover the entire sun up to Mars nicely. So we have at Mars even nice in situ measurements. So Maven has on board an instrument that is also able to observe CMEs that propagate beyond Earth. And so we can track and study the expansion and propagation characteristics of CMEs even beyond Earth. So a bit of a physics behind the CME-flare phenomenon. I already explained you about magnetic reconnection. So that means basically a reorientation of the magnetic field. There are current sheets built up due to, so we have particles that get accelerated, currents build up, and there are conditions then favorable for reorientation of the entire magnetic field. So that means previously open magnetic field closes. It closes into the direction towards the surface and into the direction outwards of the sun, so away from the sun. And in this step here, you see the closing of the field lines in the direction away from the sun, and that is exactly where the CME, the flux rope, the magnetic structure builds up. On the other side, we have the flare that is occurring here. So flare and CME, they are ultimately related to each other. And the flare basically is the particles that impinge on the denser lower atmosphere. They produce thermal and non-thermal emissions, so which we can observe in H-alpha and hard X-rays, as I already mentioned, up to gamma rays. And in the other direction, we have this propagating or erupting flux rope that has dense plasma enclosed in this flux rope. And as it propagates outwards due to an increased magnetic pressure, it can expand in interplanetary space because the ambient interplanetary space has lower pressure. So it's like a hot balloon. It starts to expand and gets bigger and bigger as it propagates in interplanetary space. And here is some cartoon of this flux rope of the shock sheath structure, the compressed plasma around, as it propagates in interplanetary space and then eventually sweeps over instruments, planets like Earth, etc. So the physics behind is a Lorentz force, a hoop force, as a consequence of magnetic reconnection. And in interplanetary space, due to the slower ambient solar wind, there is a drag acceleration. So the CMEs, they tend to adjust themselves to the ambient flow. So usually fast CMEs get decelerated and slow CMEs get accelerated. That is a very important factor for finally forecasting CMEs and for better understanding the propagation behavior. If you would like to understand the propagation behavior in interplanetary space, we also need to get the initial conditions. So that means the early CME evolution is very important, and it already tells us how fast the CME will become in the end when it propagates in interplanetary space. So the acceleration phase close to the sun is a very important point. And we saw that from observations that the CMEs that start from very low heights, so CMEs that are very so driven by very strong flares, very close to the surface, they are empowered much higher because they have a stronger magnetic field involved compared to those CMEs that start a bit higher up in the atmosphere. They have lower reconnection rates, usually are accompanied by weak flares, and they don't become that fast as the CMEs that start from very low down related to very strong flares. We also observe a mass increase in the CME, so that means also that that plasma during the reconnection process gets successively enclosed into this structure. But then beyond 20-30 solar radii, it can only lose the plasma inside the flux drop. But on the other hand, it may build up a sheath structure that comes from interplanetary space. And we all know that a change in mass is also related to a change in the drag force, because the drag force is related to the density of the structure. So we know that more dense structures are more easily propagating in a flow compared to a low density structure. So low density structures dissolve very easily and get decelerated very easily compared to a very massive and dense structure. It can propagate through a flow very fastly and doesn't lose energy and speed. So how can we forecast now the space weather effective events? As already said, we have to closely monitor flares and CMEs. They have specific relations. We came to the conclusion or found out that hard X-ray flare emission is very closely related to the early CME acceleration phase. So they are almost synchronized. As shown earlier, the particle acceleration and the magnetic reconnection process goes together. Particle acceleration produces hard X-ray emission, and the reconnection, the closing of the feed line, produces the CME body that then expands. So monitoring the acceleration phase or the flare emission in hard X-ray gives us already an idea how fast the CME will become. Besides bright emissions, we also can observe dark emissions, so-called dimming regions. The dimming regions are related to the mass that is lost, or the mass that is trapped into this closed structure. So how these dark structures evolves, it also tells us how the mass of the CME, or how massive a CME will become. So these Coronal dimmings, they tell us something about the CME speed, because we have again related to more massive structures are kind of empowered stronger. So as a conclusion from that, combining also surface parameters, so the early evolution, to observe the early evolution is a very important piece of information to better understand the propagation behavior of CMEs in interplanetary space. And this is very important because we know when we would like to forecast space weather events, we would like to know when a CME arrives and how fast it will arrive, or with which speed it will arrive. So the propagation behavior in interplanetary space is one of the basic pieces of information that we need for forecasting CMEs. A challenge, so besides knowing when and how speedy a CME is, we would like to know the magnetic field of the CME. As already mentioned before, we have a certain orientation of the Earth magnetic field. And if the CME magnetic field is anti-parallel oriented to the Earth magnetic field, we again have very strong reconnection processes and particle acceleration processes that leads to very geo-effective events. So that means the magnetic field forecasting is one of the major challenges for the future of space weather forecasting. And with that, we come to the observations again on the surface of the sun, but of the magnetic field. So we would like to know the helicity and the orientation of the flux rope of the CME as it is still on the sun, and then to observe also how this, how the orientation changes as the whole structure erupts. So with that, we can, so the magnetic flux that is involved in the flare reconnection is also one of the major pieces of information that we need to know when we would like to observe or forecast the magnetic field orientation and also the magnetic field strength of the CME. In that respect, we also can observe CMEs or flares that are not related to CMEs. So the magnetic field is a very basic parameter that is deciding whether an active region is erupting or not. So the more strong overlying fields are kind of shielding this active region, the less likely it is that a CME is able to erupt from that active region. Unfortunately, we are restricted to measurements of the photosphere. So the photosphere is the only surface layer where we can observe the magnetic field in the corona. The density is too low and the field is too weak, so we cannot really so directly observe it. So with that, we are depending on models that are simulating the overlying the coronal magnetic field. So the magnetic properties of a CME is one of the major challenges in predicting the geo-effectiveness of the CMEs at Earth. As already mentioned, we need models, and with the models we are able, as we can see here, to simulate the magnetic field. So this is a magnetic, or those are the field lines in this active region, how the negative polarity connects to this positive polarity. And from this structure, we have here some interwinding field, some twisted structure that already hints towards a flux rope that is sitting in there. And this flux rope is then able to erupt and to become a CME. And from that, we can, first of all, so the models tell us if there is a flux or if there is a flux rope sitting in that active region. From that, we also can afterwards derive the reconnected flux. As already mentioned, we derive the reconnection from brightenings, but also from dimmings, from dark structures. And altogether, we can then estimate how strong or how much magnetic flux is embedded or is involved in this evolving structure, the CME. But so we need to combine here models and observations to get the full picture of the whole thing. Likewise, not only for the surface, for the early evolution, also for interplanetary space, we need models that kind of simulate the evolution of the CME in interplanetary space. And the new sophisticated models, like shown here, is the Euphoria model. It's a European model developed over the years in a collaboration by Karl Löwen and University of Helsinki, that is then able to give the three-dimensional, this bubble structure of the CME and let it propagate in interplanetary space so that we can study the evolution of the CMEs there. This model requires inputs that come from observations like EUV images. We need the reconnected flux, so how much magnetic flux is in this flux rope embedded. We also need to know the size of the CME, as shown before, derived from white light images, the propagation direction, so to say, in the first hand, is it directed towards Earth or not? And all that is, all the information that comes from the observations is then fed into the model, and the model then uses MHD. So this model, for example, is a numerical model. It uses MHD equations to solve the propagation equations. And with that, you can then do a forecast. As I already mentioned earlier, we have a lot of uncertainties in these input parameters coming from the observational side. So also the forecast is unfortunately has a lot of uncertainty. So we are not able to precisely say when a CME and with which speed a CME arrives, but at least we are developing, so the models are developing towards more precise forecasting. So the big unknown still, as I said, we don't have measurements, only a few localized measurements of the solar wind in interplanetary space. And with that, we have to bridge the gap between Sun and Earth. And we know that most of the physics is happening there because the CME is deformed by the ambient solar wind flow. It is decelerated. It might change direction. So all those things we do not we are not able to measure. And with that, the interplanetary evolution is kind of restricted to, we have to make a lot of assumptions about the geometry of a CME. Is it a point-like CME? So you use different methods, triangulation methods even, to derive a propagation direction or kinematics of a CME. And you can also do idealized flux rope models to adjust to your image data to derive certain parameters. So the propagation direction is one of the things, and we do not know how it changes in interplanetary space. But you can, as you see here from geometry, kind of geometrical assumptions, you can derive kind of propagation directions that are okay for feeding the models. We also know that CMEs might rotate. They adjust to the magnetic field, that's for sure. As you can see here, this is due to stereo images. Stereo images are able to cover the entire Sun-Earth line, but only projected 2D images. And here is an animation close to the Sun, so that's about covering up to 20-30 solar radii, this field of view. And you see already here how structured this, so there are a lot of structures embedded in the ambient solar wind. So that's not really a CME now, so that's just the ambient solar wind that is very structured. It has some closed magnetic field inside there. So it is, it's kind of a laminar flow, but we have very different speeds, obviously. So if you track certain structures here, you find out that the speeds in the higher latitudes are slower compared to the equatorial plane, and vice versa. So it depends on active regions that are on the surface, and so how the surface is characterized at the Sun. So we see that with these, the ambient flow is not a continuous flow, so it changes, and as the CME propagates in this changing flow, also the CME characteristics they change. And with that, we also have we observe deflection and channeling of CMEs. As I said, the propagation might change due to these channels, and with that, the forecasting becomes even more trickier. So the spatial distribution of solar wind parameters, especially magnetic field and the speed, so the velocity flow, is not well known and not observable directly. So before we don't have better measurements or more complete measurements, it's hard to understand the propagation behavior of the CMEs. in interplanetary space. I already talked to you about the drag force. The drag force, that's just a small explanation here, is one of the basic parameters that we apply for deriving the propagation characteristics. And in the meantime, also we have so the disturbed solar wind conditions need to be taken into account, as we don't have a continuous flow, especially if we have coronal holes, so-called coronal holes, where increased speed is coming out of the solar corona. This all needs to be taken into account. So the structuring of interplanetary space is a very important point. And here we see, so that's a 360-degree view of the solar surface of the corona in EUV wavelength range. And again, as you remember, maybe from the first slide, you see these brighter regions, which are active regions, closed magnetic fields. And here we see a bit darker regions, large regions that are related to open magnetic field. And along this open magnetic field, high-speed solar wind streams are emanating. That means also if we have, so the slower flow comes from closed fields and the higher speed flow from open fields. And you can imagine the sun rotates, we have high speed flows, we have slower flows, and they start to interact with each other. As we have the frozen in condition, they cannot intermix easily, but they cause or produce compression regions. And these compression regions then structure the interplanetary space. So the open magnetic flux, open field, high-speed streams, it's all related to the structuring, and with that to the CME propagation behavior. As I said, the CME adjusts to the ambient solar wind flow. If we have a lot of compression regions, the CME might deflect from that, cannot propagate through those regions. And if there is a high-speed stream, the CME gets even accelerated again. That all influences the transit time of a CME and the impact speed of a CME. In the meantime, also here, combination of in-situ measurements, remote sensing data is seen here. This is a very nice coronal hole imaged here in EUV, and a combination also with models. So this dark red structure should show you open magnetic field. The green contour line is exactly the same as we derive from the image data. So the model is, in this example, only giving us not even half, a third of the open flux compared to what we actually observe. So this is one of the open magnetic flux problems that we are challenging or tackling at the moment. We try to find out how the surface structures that we observe in EUV, how related they are to really open magnetic field. But the open magnetic field we usually can only derive from models. So, but we know that the models are also not accurate. So we need to find out how to improve the situation and the understanding of open magnetic flux, and to better derive the structuring of interplanetary space. From coronal holes, so also in the group here in Graz, a lot of people are working on better understanding the magnetic field or the magnetic evolution of coronal holes. And with that, the solar wind acceleration, as already mentioned, coronal holes are the sources of strong or high-speed solar wind streams. Excuse me. And here we see in high-resolution images, or in higher, so not great or high-resolution images, but for our purposes, this is already high-resolution image. So a magnetic field information, line of sight magnetic field from HMI instrument, and we see how structured these the coronal hole. So this is the contour of the coronal hole that we extracted here. How structured the magnetic field is, and the red and blue are different polarities. So we also see that there is much more red. So there's a dominant polarity inside this coronal hole, and this leads to an unbalanced magnetic flux that then ultimately drives the solar winds, the acceleration. And by by investigating and studying those magnetic holes as they evolve, we also try to find out more about high-speed solar wind streams and about the structuring of the interplanetary space. There is, especially for solar cycle phases where we have more than one CME per day, I already explained in the beginning, we have an 11-year solar cycle, we have a few CMEs per day in the solar activity maximum phase. And you can also imagine if you have more than one CME, again, we're talking about frozen-in conditions. That means magnetic fields, they cannot penetrate through each other very easily. So there has to be some reconnection processes. So usually the interaction of several CMEs makes the situation in interplanetary space even more complicated. In that respect, the CMEs, they form complex ejecta. They can merge kind of with each other. They form single fronts. But you can also imagine if you have a lot of complex magnetic field, the orientation of the field is such, at some point you will always have an anti-parallel or anti-orientation with the Earth magnetic field, and magnetic reconnection processes are more likely compared to a very simple magnetic field configuration. So if you have complex magnetic fields and also more dense structures, as we have a few CMEs pumping into each other, the geo-effectiveness is much, much higher. So especially in terms or in times of high activity, CME interaction events are very important to understand and also to monitor, because they make the most intense geomagnetic storms. And we also had in 2017 in September, we had a very a kind of an activity phase where a lot of CMEs were erupting from the same active region. So that means heading towards the same direction, pumping into each other and making very complex complex magnetic fields that led to very strong geo-effective storms. So in that respect, CMEs that are propagating in interplanetary space, they also structure interplanetary space. So it's not also high-speed solar wind streams or only high-speed solar wind streams from the coronal holes. Also the CME themselves, they structure interplanetary space. So you can imagine if you have a river, so the river flows, there is a boat going on the river, you see how the boat disturbs this flow. A CME is in a similar manner disturbing the interplanetary space, the flow of interplanetary space. It makes a higher, so that the flow is increasing in its speed. The CME stretches the magnetic field into a more radial field compared to an inclined field as it would be during quiet times. So that all changes interplanetary space. And with that, it makes a preconditioning. And if then another CME is erupting, it faces different conditions compared to a CME before. So the preconditioning of interplanetary space is an important thing to consider when feeding also models and when doing forecasting. And so there are studies that confirm that about 2 to 5 days. So if a CME is propagating through interplanetary space, so we're talking here about 1 AU distance range, it needs about 2 to 5 days to recover from those large disturbances. So only after 2 to 5 days, the disturbed flow goes back to a kind of a quiet condition as before. And with that, so all the drag forces change and things like that. So we need to feed our models not only with those CMEs that are potentially geo-effective, but also with CMEs with large disturbances that are leaving the sun at least a few days before the one CME that we would like to forecast. So that's also a challenge for the future, to effectively feed or to give enough information to forecasting and propagation models so that we are actually able to derive a more accurate forecast for the one CME that is of interest. The preconditioning, as mentioned now several times, depends on the activity phase. And of course, it's the CME chains that are observed in solar cycle maximum. They are a rule and not the exception. So the question is maybe vice versa. Is there ever a quiet solar wind condition? Probably not. And so that makes the model performances are usually having larger errors during those times. And this needs a lot of more investigation and further development or improvement of the models. In that respect, case studies that combine remote data and in situ data, so to find out whether our image data are giving us the correct values to feed our models, we need to compare those the speeds with the actual in situ measurements. So here is a study of a single CME event where we were able to observe the kinematical profile of the CME from the sun. So starting here from the sun, and these are already in situ measurements. So here we see a jump in the solar wind conditions, in the magnetic field, in the speed and temperature, and also in the density. So that means the arrival of the shock structure. Here we see the flux rope structure. So that's the closed magnetic field that is arriving at Earth. And from that, so tracking the CME from sun to Earth and combining it with in situ data, we were able to test our models that we used for forecasting the arrival time, the speeds, the size of the CME. We can test with actual measurements to see how good our models are and how well they perform. Yeah, the good news is we are kind of in an uncertainty range that we are able to forecast by plus minus 12 hours when a CME would arrive. The bad news is how strong the impact is, and especially the magnetic field orientation. It's still that's of high uncertainty, and with that we need to basically do more research on that and to improve our forecasting. Coming finally to the impact at Earth. So there is a cascade of reactions that we actually can then observe in the magnetosphere, in the ionosphere, even in the thermosphere. So we have substorms. So that means in the tail of the magnetic field, again, like on the sun, we have reconnection processes that is then causing particle accelerations. The particles penetrate into the Earth atmosphere. With this, there are aurorae, so northern lights are related to that. In the ionosphere, we have disturbances also for radio communication. The thermosphere, the density due to Joule heating, it increases the density in the thermosphere. In that respect, satellites that are orbiting in a height of a few hundred kilometers, they experience, or they have higher drag force. That means they are vulnerable to even to slow down and then to drop out of their orbits. So they might even then drop out of orbit and hit Earth surface. We have ground-induced currents that are responsible for power outages. So there are a lot of effects that are really responsible can be responsible for major damage at Earth if we really have a very, very strong CME coming from the sun. So all that makes the space weather, studying space weather and forecasting space weather an important issue. As already mentioned, we have a lot of projection effects that makes life not easy, that has a lot of uncertainties or causes a lot of uncertainties to feed our models. And in the near future, we hope to have multiple views or side views. We already had that from the stereo mission, but the stereo mission had spacecraft that were not stable in their distance or in the orbit, so they moved away from Earth. But in the near future, we hope that we can kind of park a satellite at L5, Lagrange point L5, or even L4, so 60 degrees apart from Earth. And with that, we would have a side view that that would be enabling us to observe lower, so the CMEs and lower projection effects, and also having in situ measurements that gives us a head warning of high-speed solar wind streams. And we also have at the moment Parker Solar Probe. First data were already released. There are also papers are already out there. So Parker Solar Probe will be the first mission going as close as possible to the sun. Plan is up to 10 solar radii. So Solar Probe will tell us a lot about the solar wind acceleration, and with that about the structuring of interplanetary space. Also, Solar Orbiter was launched in February in 2020 now, and is on its way. So the instruments are on and working. And as mentioned, future ESA missions parking a satellite at L5, or even polar missions going over the poles of the sun are planned. So that all will give us much better information about CMEs and also on the flares. So in summary and conclusions, I hope I could show you a bit of the properties of coronal mass ejections, how they influence Earth atmosphere. Their properties, they are set low in the corona, so that means we need to observe the solar surface as well as interplanetary space. We need to know the source region characteristics, how they are linked to flare, to brightenings, to dimmings. Unfortunately, the magnetic field, who is the major driver of CMEs, is only measurable in the photosphere, which gives us only the very basic information, but we don't have information of the higher magnetic fields in the corona. So with that, we hope that in the near future there are better observations, or the models improved, that we can derive more reliable magnetic field information. The interplanetary space, so the structuring, the solar wind flow, is a very important point that we need to investigate more closely in the near future. And especially the models need to cope with multiple events, with disturbed conditions due to high activity phases. So that are really great challenges for the model developments. And in that respect, the modelers and the observations, they need to work more closely together, so that the exchange in information and also in the understanding is a better one, or a more close one. And with that, yeah, I hope that I could at least give you a bit of an insight into solar-terrestrial relations and on the activity of our next star, the sun. And thanks for the audience, and I'm open for questions. Thank you.
Thank you, Manuela. I'm uploading. I guess the others can use the reactions if they want to upload virtually. That was very interesting. So if people have questions, go ahead, you can raise your hand or start to talk if you want to.
Yeah, I have a question. May I?
Yeah, go ahead.
Okay, thanks very much for your talk. I learned a lot of things, but I still have a couple of questions. One is related with the sun, and another is related with the Earth part.
Okay.
One related with the sun is why the peak of the activity in general is sort of 3 years after the peak of the maximum of let's say the cycle. It used to have more activity a few years later. And the second question is related with the Earth. Last year I was trying to observe the auroras in Sweden, and I learned that the best time of the year is during the equinox. that is obviously an Earth question. It's nothing to do with the sun.
Right. Yeah.
Can you explain both things?
Okay. So as I understood correctly, first question is why there is a higher or strong activity after the actual solar activity maximum, right?
Exactly. But it used to be a few years later.
Right. Exactly. So we observe this, yeah, in every cycle. There is 2 to 3 years, as we're already in the declining phase of the cycle. There are still the major flares, major energetic particle events. The explanation for this is, or at least people assume, during solar activity maximum, we have a lot of active regions. Mm-hmm. You have magnetic energy that is built up from below or is feeding this active region. So that means to get rid of the built-up energy, you have a lot of spots. Okay. But as we are in the declining phase, the number of sunspots, so the possible ventiles to release your energy, are getting less and less. So that means there is still energy built up, but we only have 1 to 2 or 3 active regions that are able to release that energy. Okay. So the whole energy then is released by 1 or 2 active regions, and they get the major energy then. During maximum, we have 20, 30 spots. They all release moderate flares, but then still energy is built up, but we only have 2 or 3, and they get the most of the energy then. That's one of the explanations. Okay, good. And the equinox, right. So it's called the Russell-McFerran effect, and it depends on because it's related to the orientation of the magnetic field. And we have in springtime and in autumn, we have the preferred or the magnetic field is such that it can reconnect best with the interplanetary magnetic field. Okay. And so because of the inclination of the magnetic field as the Earth goes around the sun, right? Okay. Okay, thanks a lot. If you want to know more, have a look at the Russell-McFerran effect.
Great. Okay, thanks a lot.
Thank you. So are there any other questions from the audience here? So maybe I will ask one.
Sure.
So maybe that's a tricky question, but I was wondering, so how far do you think we are from precisely predicting these CMEs? And is it just a lack of observations, or
what I have told you is as soon as a CME is ongoing, so that means we already observed the CME, we are kind of as I said, plus minus 12 hours in forecasting when it arrives, plus minus 200-300 kilometers per second of impact speed, to really forecast when a CME is erupting. Oh, that needs much more time, because that's the energy buildup and the magnetic field evolution of active regions. Most of it happens below the surface, which is not accessible to observations. So there comes, for example, helioseismology into play. But also this is, we don't have enough information about the precise processes there. I'm pretty confident that the model development is ongoing very fastly, because the computational power is getting better and better. But unless we are not able to give more precise observational, values from the observations, you can have your very best model, but if you're not sure the initial conditions, it will not help much. And with that, maybe the side view in the near future will give us a bit more precise input parameters, but I'm not sure. I'm pretty sure in the next 10 years or so, we will not have a major leap in doing a better forecast. But I hope I might be wrong.
Let's hope we can get there before.
Yes. Let's hope we can get everything.
Yes.
But I would say the uncertainties from the observational parameters is too high at the moment to make more precise forecasts. and we don't have the observations to do better. Unless we fly a fleet of in-situ instruments that gives us more precise localized measurements that we can combine with observational data. But yeah, it's very tricky. Space is too large in between, and yeah.
Yes, but it's interesting you talk about helioseismology. I was wondering if there was some works going on to try to connect the interior with what's happening in the interior and this.
Right. Yeah. So there are groups that try to kind of forecast sunspots that are on the backside of the sun using helioseismology. We had with stereo, when stereo was on the backside, one could actually do the direct comparison, and yeah, sometimes it worked, sometimes not. So also the success rate was not too good, but at least they got an estimation. Yes, there is a sunspot, but to give a more precise estimation of how this sunspot will evolve in terms of magnetic field characteristics, helioseismology don't has the resolution for that.
Okay, thank you. So are there any other questions? Checking on YouTube, I don't see anything. Okay, so then I guess we'll thank you again for your talk, and
thank you for
interesting. Yes, you're welcome. Thank you again.
Thank you.
And thanks everyone for joining. So the next seminar we will have will be next Tuesday. I don't have the title yet, but I think it's something about galaxies, I think. And it will be in the afternoon because the speaker is in the US. So we'll have more information in the next emails. So thanks everyone for joining, and take care everyone, and see you soon. And thank you again,
bye everybody.
Manuela.
Bye bye. Thanks.
Bye bye.